Okay, this is Yanofsky. We're doing analysis of algorithms, chapter 7, which is all about quicksort. Okay, so we finished heap sort, and we saw heap sort in the worst case scenario is n log n. That's very good. Now we do quicksort. Quicksort, I think, was the first algorithm that really got it below n squared, and it's considered, it's a great algorithm, it's an important algorithm. Okay, a lot of the ideas we have about things in chapter 8 and chapter 9 will be using quicksort ideas. So it's an important algorithm to do. The only problem is it sometimes can be n squared, but most of the time is n log n also. Okay. Now, we studied already merge sort. Quicksort is in a certain sense, merge sort stood on its head, upside down. And I'd like to explain to you what it means. Okay? In merge sort, we easily split the numbers. We take the numbers, we split it in half, just chop it in half. Okay? And then we sort the left side, sort the right side, and then we slowly merge it together. Okay? By slowly, I mean it takes n to bring together two sorted arrays. To bring them together is n. Okay? So easily split, this is merge sort, easily split, spend time combining it. As opposed to that, quicksort, we spend time splitting it. We're going to spend most of this chapter talking about how we're going to split the numbers, but then it's easy to combine. So you see, this is a flip. Okay, let me just show you quickly the way the algorithms work. The difference between merge sort and quicksort. Merge sort, you just chop the numbers into half, n over 2. If you have an odd, n over 2 floor. Okay, sort the left side, merge sort the right side, and then slowly merge them together. That's what that line is all about. Okay, quicksort is going to be slightly different. I'm sorry, really different. You're going to take the n numbers and you're going to partition them, and some numbers are going to be over here and some numbers are going to be over there. And then what you do is you quicksort those numbers. You quicksort these numbers, and then it's going to be easy to bring them together. You'll see it in a minute. But the main point is, here you do the merge sorts and you slowly bring it together. Here you spend time partitioning it, and then you quickly sort, then bring it together. Okay, on average this is going to be n log n. In the worst case scenario, this is n log n. Quicksort on average is n log n, but in the worst case it's n squared. Okay? In the worst case it's n squared, but it's very rare for it to be n squared, and we'll talk about that at the end of this chapter. Okay, so the main hard part of quicksort, you see this is just recursive. The quicksort calls itself, so this is the quicksort algorithm. By the way, it is a 3-line program, as opposed to heap sort and merge sort. Well, merge sort is not more than a 3-line program. Well, merge is a large thing, partition is a large thing, but the sort itself is a 3-line program, so that's why it's very popular. But the partition part, we're going to spend most of the time talking about the partition. So let me show you that. Stop. Okay, so this is the partition algorithm. This is the algorithm that splits things up. It's a little bit painful, so we're going to go through it line by line. But basically what it does is, it takes your array, A, which is part of the input. It starts at P and ends at R. So this is array A, starts at P and ends at R. And it splits it up into two parts. Those things less than the pivot, those things more than the pivot. The pivot is right here. Okay? And basically what happens is, it goes through the array like this. This is position J. Okay. All the elements in here are less than or equal to x. All the elements in here are greater than x. Okay? And in here is not seen yet. Okay? So we start off here and we didn't see anything. And slowly but surely we're going to pivot. So x is equal to a of r, that's the last element. We're going to pivot around that element and put those things that are less than x in here, those things that are more than x in here, and then keep on going until we get to the end. And then again, what's going to happen is you're going to split, the array is going to be split someplace. All the things less than here are over on this side, all the things more than here are more. Okay, so let's go through it. Partition, A is the array, P is the starting point, R is the ending point. X is equal to P of R. That's the key that you pivot around. That's the thing that you split the array into two. Okay? I is equal to P minus 1, so you start off on this side, and you do as follows. For J is equal to P to R minus 1. You pretty much go, this J goes along from the beginning till the end, till X. We don't have to check around here, and here's what we do. If A of J, that's the thing that you're looking at as you go along, if it's less than X, then here's what you do. Move I is equal to I plus 1. I was over here, now move it over here. That's your boundary between what's less than X and what's more than X. So if you found something that's less than X, you have to increase your boundary and put it in this part. Then you exchange A of I for A of J. We'll do it with cards in a minute. Okay? And you keep on going and keep on going. Okay? Those things, I is at places where it has to move it to this side. So you're going to see as we go along. At the end, it's going to look something like this. You're not going to have anything not seen anymore. And so at the end, you're going to have something like this. Here's your I position. All these things are less than X. Okay? And all these things are more than X. And at the end, you swap this. Put X over here. So all the things less than X, X, all the things more than X. Okay, and this is going to be something that's more than X. Okay, and you do it. Okay, so let's do it with these cards. Here I have 5. Let's pivot with these cards. So basically, we start here. I is here. P is here. We're pivoting around 5. So 5 is our main card. Question, is 3 less than 5? Yes, it is. So what do we do? Okay, well, basically, I is equal to I plus 1. We exchange I and J. Well, we're going to change 3 for 3. 3 is less than 5. We leave it alone. Okay, is 6 less than 5? Answer, no, it's not. 6 belongs on that side, but we don't do anything. Now we do 7 more than 5. Yes, 7 belongs on that side. That's fine. Okay. Now, let's do this. So basically, this is our boundary. This is our I. Is 2 more than 5? No, it's not. 2 is less than 5. And so what we do is we swap it. We swap it with what? With 6 and 2. We swap that. Okay, that's this exchange. Let's go on. 10. Is 10 less than 5? No, it's more. Is 8 less than 5? No, it's more. Is 4 less than 5? No, it's 4 is. So what we do is we swap it. We go like that. King and queen is more than 5, so we leave that alone. And then the last thing you do is your I is over here. That's the last thing we change. You swap it like that. Okay, now when you look at this, you'll see these are things that are less than 5, not necessarily in order. These are things more than 5, not necessarily in order. And so we're not going to bring them together. It's not going to be in order. We're then going to quicksort this and we're going to quicksort this. The main thing to keep in mind is that when you're quicksorting, your pivot element is very important. For example, if I pivot element this with this 6, I'm not going to do very well. Basically, at the end, this will go here, and everything here is more than 6. There'll be nothing less than 6. So we're going to do another example of this partition algorithm. It's a very nice algorithm. Question, how much work is done? Well, basically what you're doing is you're doing this loop from the beginning of the array to the end of the array, or the end of the array minus 1. Okay? And so you're doing it, and each time you're doing basically just one exchange. So this operation takes, this program takes 9 n times. Okay? I don't want to do it with that. I want to do it with this. Okay, so let's do this. We're going to pivot around 8. 5 is less than 8. Let me make sure that this camera can see you guys. Holy cow, sorry. Okay, sorry, that was a big mistake. Okay, guys, now we have to do it. We're going to pivot around 8. Okay, sorry about that. I'm not going to mess it up. Pivot around 8. So 5 is less than 8, leave it alone. 7 is 8 less than 8, leave it alone. King is more than 8, so it goes on this side. That's fine. Queen is more than 8. 6 is more than 8. 3 okay. Anyways, what's going to happen is this is going to go. I'm sorry, 7 is more. 3 is going to go here. We're going to swap with that. Queen is going to go there. 2 is going to go there. Okay, and 10 is going to go. No, 10 is okay. Okay. Then when we're finished, we're going to swap it like that. Okay. Anyways, you're going to see it working in the algorithm. Okay, so that's partition, and then. So again, you have to go through it. I'm sorry I messed up the first time, but you'll follow it. Basically, it's not so bad. Okay. Then the quicksort algorithm is as follows. Just doing it. I wrote it already, but I just want to do it in a little bit more details. If P is less than R, that means if the beginning of the array is less than the end of the array, then Q equals partition A, comma P, comma R, quicksort from A, the array A, from B, P, the beginning, till Q minus 1. Okay, there's no reason to partition the pivot, and then quicksort the other part. A, comma, Q plus 1, all the way till R. That's it. Okay, how much work is done? Very simple. On average, well, it depends how much you pivot, how much you split it into. Okay, so let's see what happens in a good case. In a good case, you'll pivot around something somewhere in the middle. So you'll have something like this. You'll do n operations in order to partition, and then you're going to have t of n over 2 for the left side, plus t of n over 2 for the right side. Okay, we've seen that before. We've seen that a few times before. That's equal to n log n. Okay. But you know what? You could get a bad pivot. What happens if you pivot around 10? So then on this side you're only going to get Jack, Queen, King. On this side you're going to get 9 cards. So that's not very good, but let's see what happens then. Well, in that case, it's going to be something like this. Let's say you do a lot of pivoting, you do a partition algorithm, so it takes you n to do a partition algorithm, but it turns out that after you partition, you get something like this. One-tenth of all your stuff is over here, of all your cards is over here, and 9/10 of all your cards are on this side. Now, you're going to have to do a lot of work on this side. That doesn't help you a lot because most of your cards went out. So you can think of it like this. You have a giant set, you have a few things here, and a giant set over there. So now when you recursively call it, these things get smaller, but if you have a bad pivot, it doesn't really work. Okay? So this is called a bad pivot. The book spends a little time, not really in our sections that we're responsible, and more in the later sections, section 7.4, where it shows that even in such a case, you know what? That's still, even in such a bad case where you have bad pivots, it's still n log n. So that's an amazing thing, because even when you have bad stuff, still things work out well. That's very nice. Okay, but you can have it really bad. Let's say you have n cards, okay, and you pivot, and on this side you have 1, 2, 3 elements. On this side you have n minus 3 elements. So only 3 cards here, and here a lot of cards, n minus 3 cards. Well, it's going to turn out, this takes a little bit to sort, but this one is going to take, you're going to have to split it up. Now again, let's say you have bad cards. You have a bad pivot here, and you only have 1 card here. So this is going to be n minus 4 cards. Okay? So in this case, what's the worst thing that can happen? The worst thing that can happen is you have n cards to sort. You partition them time n. It takes you n things to partition them. And the worst thing that can happen is you have t of n minus 1. You don't get anything on this side, and you get something n minus 1. Well, we did this example. This was the first example we did. It turns out this is n plus n minus 1 plus n minus 2 plus n minus 3. This is the Gauss trick, and it turns out that that's equal to n squared. Okay, so that's n squared. Okay, so Quicksort, the worst possible thing can happen in Quicksort is n squared. That can happen. Can we protect from that? Okay, it can happen n squared, but it doesn't happen often. So again, on average, Quicksort is n log n. In a bad, if you have bad partitions, it's still n log n. But in the really worst case, or in very bad cases, it can be n squared. Question: when does the really bad case happen? Okay, so let me show you. Let's say I have a bunch of cards. Okay, can you see the cards? Yeah, you can see the cards. Let's say you have a bunch of cards, and they're kind of in order. Then I want to add in 2 new cards. So here's what I do. I place the 2 new cards in the beginning, and I say, you know what? Let's sort it right now. Okay, so this is the typical thing. You have a list of your customers for your store that you're buying, and every month you go at the end of the month and you add in all the new customers that you have, and you add them to your list. So you have an alphabetized list of customers. Okay, so you have add in a few things. Now, if I pivot with this card, I am not doing well. Why? Because it's going to make everything less than the king and a few things more. So updating an ordered list and then pivoting with your last card doesn't make sense, because your last card is your maximum card. You're not going to partition very well if you use your maximum card. So Quicksort is not very good at maintaining a list that's almost already sorted. Okay, so this is what we said. We're not only analyzing out, we're not only showing algorithms, we're analyzing when is it good to use it. Well, it's not good to do that. Okay, in contrast, if the thing was totally unsorted, then you might want to use the last thing. Okay, so that's an interesting thing, that Quicksort can have the worst possible case, can happen when it's totally sorted or when it's very close to sorted. That's an interesting thing. Okay, now here's the solution. The solution is in section 7.3, it's called randomized versions of Quicksort. Let me show you what that's about. Okay, but beforehand, let me just give you a brief overview. You see, computers are very good because they do everything exactly as they're supposed to do. They're deterministic. You tell them to do things, it does it. It doesn't flip a coin, it doesn't, randomly think about things and stuff like that. That's what human beings do. And so that's the power of computers. They do things in a set way. But we're going to see something actually very shocking. Okay. Here's a bunch of cards. And you can see the cards. Okay. If I use this as my pivot card, it's not going to be very good because it's 10, it's a high number. So in section 7.3 they make the following suggestion. Randomly pick another card. Randomly pick another card, exchange it with the last one, and now do randomized quicksort. Now do quicksort right there. That's called randomized quicksort. You don't choose the last card as your pivot. You choose a random card, thinking that the random card you choose might be somewhere in the middle. Okay? And in fact, 5 is somewhere in the middle, so it's going to split the cards halfway through. Okay? What can go wrong here? Okay, so again, the purpose of doing that is you're going to split the array better than if you have a bad pivot. Okay, what can go wrong? Well, I can randomly choose a card, and I'll choose this one. The king is over there. Now, if I use that king, what happens? If you use the king, it's not going to have a good pivot. So randomize, even using the randomized thing, you can still have the worst case scenario. And in the worst case scenario, it's an n-squared algorithm. So again, quicksort is n log n on the average case. In the very worst case, it could be n-squared. There is a way of preventing the n-squared by randomly choosing some card in the middle, and you think that if you randomly choose some card in the middle, you could maybe do better. Okay? But even when you randomly choose some card in the middle, you can still get the worst case. Why? If you randomly choose the king, or you randomly choose some high number from the middle. Okay? So here's another suggestion. This is mine. It's not in the book, but it's in mine. Here's another suggestion. You have an array. You want to pick some card that you know that when you partition, it won't partition. So rather than picking one card over here by random and then pivoting around that one card, why don't you do the following? Pick 3 cards. Okay, so let's say this is 6, this is 8, and this is 5. Randomly pick 3 cards. Okay, then put them in order, choose the middle one. What's the middle between 6, 8, and 5? And the answer is 6. Okay, now put that at the end. The one at the end, put that at the end, and pivot around that card. Why? Because you chose 3 by random. What you're going to make sure is probably you're not going to get, by using the middle one, you're not going to get one of the closer ones. Okay? And so you're going to get something that's far away from the extremes, either 1, ace, or king. Okay, obviously this can also backfire, but it's going to be a lot harder to backfire. If you randomly choose 3 cards, okay, and they happen to be Jack, Queen, and King, then you're going to pick what's in the middle of Jack, Queen, and King, and the answer is Queen. Okay, and you put the Queen at the end and you pivot around the Queen. That doesn't help you. But the chances of randomly picking 3 cards, and all 3 of them are such high cards, is very, very rare. So again, quicksort is an n log n algorithm. and it works very well. Okay, it can get, in the worst case, n squared, but we have ways of protecting it to make sure that it won't get to n squared unless really bad things happen. Anyways, so that's that. Next time we do chapter 8. Chapter 8 is called Sorting in Linear Time. Not n log n, but down to n. Show you. Have a great day.